start just so today I will introduce von Neumann entropy, which has various uses in quantum information. That is kind of the first half of the lecture. And actually we had planned to go into quantum computation already in this lecture as per schedule. So we will go do that in the kind of the second half. Okay. But before that, I need to introduce just give you a very fast motivation, really without any proof, kind of more like a physical motivation for it. Okay, so how do we measure information in the first place? Okay, so suppose you have say first we just want to measure uncertainty. Okay, and there are a certain number of events occurring with probability say Pj. Okay, so event j, say there is an event j, just think of classical events. Okay, event j occurs with probability of Pj, and suppose all these Pj's are not the same. Okay, so some have more chance of occurring. Okay, so suppose an event has a very large chance of occurring, like half. Okay, then it makes sense, and so suppose I have considered the following things. So suppose there is an event E1 which has chance half, event E2 which has chance a quarter, event E3 which has and E4 which have chance 1/8 each. Okay, then it is not very, so there are 4 events, so obviously you can use 2 bits to send that information 1 of 4, but there is a more economical way to do it. Okay, so makes sense, when I mean makes sense means it's economical, is that the largest event, okay, you want to spend the least bits. So say it is just encoded in 0 in a single bit. Okay, because it will occur a lot of times. Okay, then E2 you actually encode with 2. Okay, so 1 0, these are called prefix codes, so that there is no confusion. Okay, and then this one you do 1 1 0, and then this one will be actually this one can be just 1 1 1. Okay, so is there a, okay, so no, so this is probably 1 1 1 0. Okay, so you see sometimes we are using more in number, but since their probabilities are far less, okay, then in the end you win. Okay, when there are more events and things, you will see I don't know exactly whether this one I have written right, but another thing you have to be careful is that you do not confuse, so everything is ending with 0, so that when you find 0 one code has ended. Okay, so you are saying a series of events E1 E2, there is no chance of confusion. Okay, so that's why it is like this, and hopefully even in this one you though you use more with some probability, on average you save to be more than 2. Okay, you can calculate that and check. The general rule is, of course these I have taken like these, probabilities need not exactly be that, so you do in approximate sense. So the general rule is this: if probability is like that, then it makes sense to encode in nj qubits. Okay, nj bits. Okay, so that you use the least amount of bits on average. Okay, so how many bits on average you need to encode something? Okay, so this nj is nothing but equal to log to the base 2 of 1 by pj, right? Okay, so the average number of bits that you need to convey to know exactly which event had occurred. Okay, if they were occurring with different probabilities, then the average number of bits, okay, is given by, okay, the probability of each event occurring, sum over j, okay, log 2 of this so into nj is just log 2 of 1 by pj. Okay, so this is called the Shannon entropy. Okay, minus sum over j equal to pj log 2 pj. Okay, so this is the number of bits you need to convey to go from an uncertain situation to a certain situation. So after on average getting this number of bits, you will know exactly, say E3 has occurred. Okay, so you will have your uncertainty will decrease. So that means also that it is a measure of the uncertainty. Okay, so the Shannon entropy is a measure of uncertainty in number of bits, in the sense that this is the number of bits of information that you need to gain, okay, in order to be sure of what had happened. Okay, now let us go to the quantum realm. Okay, in quantum realm, okay, the events, okay, the events are being replaced by quantum states. Okay, so here I use the word events, but they are conveying information, so they are a bit like you know, letters of the alphabet. Okay, for example, the entropy of English is not really the maximal it can be for 26 alphabets. Okay, 26 letters in the alphabet, it's far less because they have different frequencies of occurring. Okay, and so on average length that you will need to you know, convey one letter of English is probably far less than the total number of bits needed to do those 26 letters. Okay, now in quantum mechanics, these letters become quantum states, so there's more uncertainty in them. Okay, so for example, we can write a quantum density matrix rho as sum over j, again like pj. Okay, but now these states psi j, okay, which are not necessarily orthogonal states. Okay, so these psi j's are not necessarily okay. So what do you think will happen if they are not necessarily orthogonal? Okay, means they are not as easily distinguishable, say, as A and E, right? They are a little bit less distinguishable. Okay, so there should be I should be able to learn it should be less uncertain than that one, right? Now some properties, so this is in quantum mechanics. Okay, now some properties of density matrix make our task very easy. Okay, so it can exactly become something like that. Okay, in a very because of some convenient properties of the density matrix. We know density matrix is Hermitian, okay, and with positive eigenvalues. Okay, this is just a short for that. Okay, so what does that mean? That implies that the density matrix can be written, okay, as sum over j, lambda j, okay, and some orthogonal eigenstates. So these are really the eigenstates of the density matrix. These we know are each greater than 0, so they are like the probabilities. Okay, so so these are the eigenvalues. Okay, they are exactly like those probabilities. Okay, so now my pj has changed to lambda j. Okay, and these are orthonormal. So in fact, they are like letters of English. Okay, so what is the uncertainty here? So how much do I need to learn to be exactly sure which lambda j it is? Okay, when I'm sure I've just really got a ket. Getting a ket means you are perfectly sure of the state. Okay, so that means that is equal to, that is called the von Neumann entropy of rho. This rho is minus of this, so minus of j lambda j log 2 lambda j, okay, just as before. So it's the Shannon entropy in the Eigen basis. Okay. And that is a very important thing in quantum information. So it quantifies the uncertainty in the initial quantum state. It takes care of the fact that some of the things may be not orthogonal to each other. Okay. So you just rewrite the thing as if it's a classical probability distribution in the Eigen Basis, and that's called your von Neumann entropy. Okay. So of course, the more familiar form, it is written in this form, is minus trace of rho log to the base 2 rho. Okay. So in the Eigen Basis, that's exactly the same thing. Okay. Now, right. So this has a few interpretations. So one interpretation comes immediately from the definition. Okay. So it is the uncertainty in bits in ensemble, in a quantum ensemble. Okay. So ensemble means that suppose you have a thermal state or something, right? So of course in thermal state you already have it in this form. So but you may have some other state, some uncertainty, and it will tell you the number of bits necessary to reduce it to a ket, to a single ket. Okay. So that interpretation comes just from the definition, but there are a few other quick, other applications which I'll quickly tell before moving on to the main application, which is in entanglement quantification. But so one of them is that classical communication via quantum states. Okay. Or quantum channel. Okay, that also, that's where von Neumann entropy also comes. So suppose you now have non-orthogonal, so exactly that kind of thing. So with probabilities Pj, okay, you have non-orthogonal, alphabet, non-orthogonal letters. Okay, psi j. Non-orthogonal letter psi j with these probabilities Pj. Okay, then what is the best classical communication you can do with them? Okay, so it's like someone has got an English alphabet bag, okay, and can send letters to the other party. Only handicap is some of the letters all the letters are not perfectly distinguishable. Okay, they are not orthogonal. Okay, then again von Neumann entropy is the number of bits. Okay, so S rho bits, okay, per letter sent. Okay, no, per transmission, per letter that's sent, this number of bits can be sent. Okay, where the rho is now the same rho as that, sum over j, okay, Pj psi j psi j. Okay. This is called the Holevo-Schumacher-Westmoreland theorem. I mean, of course, I am not proving theorems here at all. Okay, so these can be proved, rigorously, but I am just giving the heuristic justification. Okay, so to Westmoreland. Okay, so these can be proved more rigorously. Okay, now it also has an application when with Pj you have mixed states rho j. Okay, so instead of psi j's are as you say non-orthogonal, but suppose they are even mixed states, so they have a little bit of statistical uncertainty as well. Okay, then again the formula is it was proved by Holevo long time ago, and it's very simple. It's just the classical capacity for this is given by S of rho, which is the same, would have happened if they were pure states, but you see each one you receive has some uncertainty left. Okay, so those bits are things which you are not receiving. Okay, so you say summation over j, okay, Pj S of rho j. So you subtract away. So each of those, rather than now receiving a ket psi j, which you would perfectly be certain, you are receiving a rho j, which still has some uncertainty. So that is not the amount of information you can receive. so you subtract away, and this is the achievable classical capacity of a quantum channel. Okay, this is called classical capacity of a I have written quantum states, but it's called of quantum channel. Okay, assuming that through a quantum channel means you are sending quantum states. Okay, this actually, the rigorous derivation of this is also not that difficult. You just have to take the mutual information between orthogonal states on the side of Pj, like classical states, correlated with some non-orthogonal or mixed states rho j, and that mutual information just comes out to be that. Okay, so it's kind of an easy derivation, but I'm still not doing that here. Okay, so this is one of the applications of von Neumann entropy on classical capacity of a quantum channel. Of course, people particularly would not necessarily want to do that, right? Use quantum states to send classical information. Another is called data compression. Schumacher did that first, and in that same paper, or one of those papers Benjamin Schumacher did, okay, quantum data compression, early 90s. So these were developments kind of in parallel with quantum computation. So quantum information theory was not necessarily particularly tied with quantum computation that time, but he invented the term also. I mean, it's a historical thing. He invented the term qubit in one of those papers. Okay, quantum bit. Okay, and what he said is that if you, and again it's kind of somewhat an obvious statement if you think of it, okay, but it can again be proved, is that this kind of ensemble, okay, say you wanted to send that quantum thing now to the other side, okay, but with minimal number of qubits, okay, then you can do it with, so n copies of that can be sent with n into s rho qubits. Okay, so n suffice can be compressed, suffice for, okay, n to accurately send rho to the power n. So you have n copies of rho on one side, where rho is this kind of thing, not necessarily with orthogonal states, but certain density matrix, okay, will have a certain von Neumann entropy. You can compress, and instead of sending n qubits, you can send a fraction n times. This is always a number less than 1 for a single qubit. So that fraction of qubits sending accurately through the channel is enough. On the other side, you can take some empty qubits and again like reblow up the state to that. Okay, so no, it is always worse than the classical channel, right? Because so particularly people would not necessarily want to do that. Yeah.
Because of the probabilistic nature.
Yeah. If you had fully orthogonal states and they went perfectly, then of course it's equivalent. But in general, people will not want to do because of probabilistic nature that these are non-orthogonal. Okay, but this is a capacity people can compute. Okay, so that's why it's far more computable than the number of qubits you can. So the quantum capacity is a notoriously hard thing. Okay, so we will touch upon that very soon. Okay, that also can be done through von Neumann entropies. Okay.
But is this saying that suppose I wanted to store the number 100 in a quantum computer as opposed to a classical computer?
Right.
Require more resources?
No, in particular a quantum computer you can just, I mean a classical computer is a sub in this sense without considering the issues of decoherence and all those. A classical computer is always a subset of a quantum computer, so you can use an orthogonal set of states. Okay. Yeah, this is telling that if you were already given this, the letters were non-orthogonal letters in English. Okay. I mean, people will not necessarily want to communicate in that way. Okay. Now, right. So let me go to the next step. Okay, so these are two applications of few applications of von Neumann entropy which can be kind of argued for. Okay, you don't need rigorous proofs to see. For the application on entanglement, I'll show you how it very naturally emerges out. Okay, of as the quantity to quantify entanglement. Okay. So consider this kind of scenario which I have drawn quite a few times in the past classes, but I never got to do much with them. Okay. So but now consider just pure states. Okay. Okay. First something to establish. So we have established these units. Okay. So this kind of state psi plus, say, which is say a maximally entangled state, this kind of state we are saying has an unit of entanglement. Okay. This is useful for perfect teleportation. As we know, we ascribe it like one unit. Okay. Now if we do that, you can very easily see that if so these are really some basic precursors I am doing now. So if you take a state which is shared between two parties, and just for brevity of time I'm doing it quite a bit faster than I usually do for these things. Okay. Suppose you had many states shared between Alice and Bob, all psi plus. Okay. Say you had small n of those pairs. Okay. Then what is the entanglement? Entanglement is n e bits. Okay. Right. This is just because they are separate pairs. Okay. Each has one e bit. Okay. So you can teleport n pairs, so it has n e bits. Okay. Now this thing can be rewritten mathematically in the following form: 1 by root 2 to the power n. Okay. Now sum over j equal to 0 to 2 to the power n minus 1, and then you write on the side of a, you write everything. Okay, from 0 to so there will be j on a side and something like, so whenever it's 0 there's a 1, so we can write it as like a j complement, yeah, on the other side. Okay, so it's like all zeros on a side, so all ones on b side, then single one flips, so it's a trivial rewriting. Okay, which generally means that if I write this like that as a general d-dimensional, small d-dimensional system, j equal to 0 to like this small d minus 1, okay, j b, okay, this means a d-dimensional state with going over equal amplitudes over all the d states. How much entanglement does it have? Okay, it has, you see, d is log to the base 2, so it has n e bits, but n is log to the base 2 d. Okay, so this has log to the base 2 d e bits. Okay. So this is a fact which will be very important in what I write, that if you have a general d-dimensional system, a qubit equal superposition, 0 0 plus 1 1 plus 2 2 up to d minus 1 d minus 1, then the entanglement is just log to the base 2 of d. Okay, that just follows because we can rewrite n pairs as 2 qubits of that dimension. Okay, it's just a equivalence. Now we are going to show another equivalence which is less trivial. Okay, so this equivalence is This equivalence is between far less entangled states. Okay, so suppose we take states, we want to quantify the entanglement of things which are like alpha 0 0 plus beta 1 1. Okay, suppose something like that. Okay, how will we do that? That's the question. Okay, so these are imbalanced. Okay, now we take many of those. Say we take n of those things. Okay, so this is the first one is alpha 0 0 a1 b1 plus beta 1 1 of a1 b1. Similarly, there will be a2 b2 and up to there will be things of up to an bn. Okay, so there are n copies of these things. This is Alice's side and this is Bob's side. Okay. Now, what they can do is they can do local operations on these sides and classical communication between them, okay, and try to get to these units, okay, and how many units they can get to, okay, will be a quantification of their entanglement. Okay, but there is more to it here. Actually, you have to almost do nothing. Okay, it's not that they are throwing anything away. You will see. I mean, they will throw something away, but that is kind of innocuous. Okay, so let's just think about these states. Okay, so these alpha and beta, I'm going to write slightly differently, just because I'm habituated teaching in that way. Is square root of p and square root of q. Okay, where p plus q is 1. Okay. Okay. So just the amplitudes. Okay. Of course, there could be complex numbers and everything, but those could be absorbed inside the definitions of the states. Okay. So it's root p, root q. Okay. I should have also taught. I didn't mention Schmidt decomposition. So in general, whatever quantum state you have of 2 qubits, you can always write it in this way. Okay. Of any 2 quantum systems, in fact, you can always write with a set of orthogonal things basis in first and set of orthogonal basis in the second one. Okay, that is called Schmidt decomposition. Okay, and it's the same statement as singular value decomposition. Okay. Now, suppose you have this p plus q equal to 1. Now, on each side, okay. Sorry. So I forgot to mention the reduced density matrix. Okay, so which we will also need. Okay. Okay. So you see here what we are asking. There's a question we are asking here, that what is the quantum state of one part, okay, and we have a bipartite system. So how do we find that? So usually you try to ask, so this you should construct an entity which suffices to get all probabilities, okay, correctly. So if you put that constraint, you take a whole density matrix and you put the constraint that local probability to jump to any particular say state, say m, should be the same, okay, should be predicted correctly from an entity which is completely local, then automatically you get the entity to be this thing, that rho of A, okay, is equal to a complete sum over a complete basis of the second system B KB, okay, of rho AB, and this thing is called the reduced density matrix. Okay, so simply the partial trace, we call the partial trace over system B rho AB. Okay, so this entity suffices to predict all the probabilities correctly. Okay, even if you predict it from the whole one, and this one you will get the same values. Okay, that's why you use this. Okay, now so if you compute the reduced density matrix of this A side, say any one of them here, okay, say rho of A1, you can see it is with probability p in 0 and with probability q, which is nothing but 1 minus p in 1, right. So, locally at least Alice is thinking in that way, okay, of course not measuring, but that is what available to Alice. Okay. So, now we use laws of probabilities, okay, and typically what we will use is this thing called typical sequences. Okay. So, if this small n is very, very large, okay, what will a typical sequence have? The error for deviation from that typical sequence will go down as 1 by square root of that small n. Okay. So, essentially typical sequences will have np zeros and nq ones. Okay. All other atypical sequences probability will tend to 0, okay, as 1 by square root of the ensemble size. Okay, they will just not be there. So, if you take small n to be sufficiently large, this is kind of equivalent to exactly that typical subspace, okay, the subspace which has np zeros and nq ones. See, you did not do anything, you are just ignoring the very low probable things, and they can be even less. More larger you size, that is an even smaller fluctuation. Okay. So, the whole thing given large enough memory is just those states. Okay. So again, I am not doing maths at the level of rigor as there are there in these proofs, but the basic idea is that. So, essentially the whole state, I have really not done anything, the whole state is equivalent, to this thing. 1 by square root of n choose np, okay, and sum over all these typical sequences are equally probable, okay, sum over, okay, what is it? So, n sorry, so give me a moment. Okay, so we have this many terms, okay, and each term is like each term has np zeros and nq ones, and they are all kind of equally there. You see, I'm trying to establish this equivalence with the qdit. Okay, so there are essentially the number of terms is j equal to 0 to n choose np minus 1. Okay, you agree that there are n choose np terms where I have np zeros. Okay, and of course, this is just a complement, so those have nq1s, and those are the only terms which are important. All other terms, so this state is that this equivalent to this plus kind of epsilon, yeah, which is of the order of say 1 by root n, which kind of with blah blah, okay, which we kind of throw away. We don't care about that. Okay. So, it kind of becomes equivalent. So, let us just not think about that at all. Okay. So, now following this prescription, how much entanglement is there? So, this is, you see, a large qdit, okay, but the qdit is not of the whole dimension small n, but the dimension of n choose np. Okay. So, the amount of entanglement in these in this collection, okay, this collection is log to the base 2 of n choose np. Okay. Now, you can kind of guess what I am going to do, okay, to bring these things to n log a p log p kind of forms, right. It is a very famous approximation people do, because I am going to get factorials, okay, but I want n log n kind of things. Okay. So, I am going to use this Stirling approximation. Okay. So this is log to the base 2 of n factorial minus log to the base 2 of np factorial minus log to the base 2 of nq factorial. Okay. So then what's going to happen here? Okay, so this is n log, we are taking large n log n minus np log log to np plus, okay, plus np minus nq log to nq plus nq. Okay. So you see the n cancels, n cancels with these nicely, and then n log n minus n. So there is, okay, so there is also that term you can write it as log n plus log p. Okay, so that will cancel with this one, so you will be left with minus n times, okay, p log to the base 2 p, okay, n times minus p log p minus q log to the base 2 q. Okay, so this collection has n times this amount of entanglement. Okay, so this is nothing but n times the von Neumann entropy of the reduced density matrix. So I have erased that now, but the reduced density matrix after partial tracing of the first one. Okay, that, so essentially the density matrix of A, okay, is the same as in this case as the density matrix of B. So that amount of entanglement is there. Okay, so these n actually has a fraction of entanglement which is n times s. Okay, so then this s, von Neumann entropy, is equivalent to the amount of entanglement this thing has. Okay, yeah, I have really not done anything to the state. I have just rewritten it in some sense. Okay. And in some sense, the Schumacher data compression of qubits I was telling is the same thing. Is the same thing done to an entangled state. Okay, so this was proven by Bennett, Schumacher, Popescu, Wouters, or something like that. Okay, in a long time ago. Okay, and then Sandhu Popescu wrote a paper later on justifying that under some reasonable postulates, this came out to be the only unique entanglement measure. Okay, but I like this more because this is more like a constructive proof rather than a proof coming from principles. Okay.
Is this in some sense the extensivity of the entanglement entropy if there was a typical sequence?
Yeah, I kind of used extensivity in the sense that I use the products are the same. Okay. So then I particularly did not use extensivity anymore, rather than that it's the sum of those. I mean, these were completely independent pairs, so it's a good assumption to assume that it is they are adding up. Okay. So there are things which become complicated when we go to mixed states. Okay, so this operation is not reversible anymore. So anyway, now is the time to shift to mixed states actually. Okay, maybe I will have to start quantum computation in the next lecture and just do mixed states in this lecture. Let us see how it goes. Okay. So okay, so now we also we gave an example in the last class of this thing called entanglement distillation, which was a picture very similar to that. Okay, here you see there is a picture very similar to that here, in the sense that here, but here it is not doing some actions to go between them. Here it is really equivalent to a fraction of n times S rho of perfect entanglement, okay? Because as we said that this entanglement of a qubit like that is convertible to, you know, that many. Yeah? So that fraction of maximally entangled states is that, okay, with some in an appropriate reinterpreted basis, this typical sequence basis, okay, and with some extra garbage, okay. In case of mixed state, you do this procedure as I told in the last class by upgrading entanglement, maybe pairwise or some procedure, and reach this scenario, but it's not an equivalence. You throw away some entanglement on the way and you cannot get it back, okay. So that is a problem, okay. So that is called distillable entanglement. Then that's also a fraction, n times the distillable entanglement, but no closed form formula is known for that, okay. But again, entropy plays an important role in the sense that there is a bound which can be done in terms of that, okay. But we will come to that soon, since I kind of showed distillation already in the previous class, where these would have been actually mixed states from a channel, and then you do some you know, actions together to reach something like that. That thing, then that thing which we call distillable entanglements, okay, distillable entanglement now of the whole state rho AB, okay, also given by von Neumann entropy differences. So it's given, so this is called the one-way distillable entanglement. You can communicate only from Alice to Bob and not back from Bob to Alice, because this is the only one people could compute, okay, is known to be bounded by the so-called coherent information. And what is coherent information? That is equal to the S of rho B minus S of rho AB, okay. So you see it perfectly matches in the case of pure states, okay, to the von Neumann entropy. For pure states, this term will be 0, and the distillable entanglement, in this case for distillation we didn't have to do anything, we just reinterpret it in the typical sequence basis, the state, okay, is that. But when you have mixed states, you have to subtract this, okay, and this is an achievable lower bound in one-way communication, okay. Okay, so why is this? Again, this is heuristically understood in the following way, okay. Remember, you can interpret this, say how do you interpret a mixed state, okay. For sake of time, I am just going to kind of replace some symbols here. Don't get confused, this is a different part of the lecture really. So suppose you had rho A1 B1 and say rho AN BN here, okay, so many copies of that, okay. There you can always interpret as a pure state after enlarging with another environment, E, okay. So it's like a psi AB, so you can just enlarge Bob's part, okay, and then you can make a pure state with Alice and that thing, okay. The distillable entanglement of that thing will be this, because then it's a pure state, right. You can distill, Alice can distill with environment Bob combination, the state is can be reinterpreted to have this much amount of entanglement. Alice has with environment and Bob, but from that you have to subtract the amount of, so these rho ABs, okay, they themselves have an uncertainty, okay. When we are going to this scenario, we are not only estimating the entanglement, but we are also purifying it, knowing exactly as a ket. So at least that much information we have to gain, these many bits of information we have to gain to make the mixed state rho AB to a pure state, and on what you can distill, from just one side would have been that. Okay, so you have to kind of subtract away these amount of bits we have to gain, and here the assumption is each time you gain that those many bits, you kind of destroy some entanglement, that many bits of so you cannot measure the states without destroying one unit of entanglement. Okay, so that is kind of the heuristic logic. Okay, and then people define quantum capacities which are very similar. Quantum capacity is the same as how much entanglement you can generate because of teleportation. So number of qubits you can send per use of channel. They are defined as regularized versions of this. Regularized means you take n copies and see what you can do. I have to finish now, right? Ah, okay. Oh, okay. Okay. Yeah, so we can finish. Okay, okay, okay. We can. Okay, okay. What is the time now? Okay. 3:50. Ah, okay, 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 okay. So we are nearly done. Okay. So let me just then say that for mixed states we define entanglement in a different way. So let me just define what a mixed state entangled is, and then I will stop. Okay. So when you have mixed states, okay, you can of any particular system, suppose you can write it as a sum over j pj, okay, of something like a rho j system A cross rho j of system B. Okay. So suppose you can prepare, so how can you prepare these systems? So you have two planets and you have bags of states. Okay. You can just call each other up and prepare those states, okay, and do not need to send any qubits. Okay. So these are called separable states. Okay. And just for the sake of time I erase this. When it is not that, okay, that means to create that state you must have had to transfer some qubits from one side to another. That is called an entangled state. For mixed states, this is the definition of entangled states. Okay, and the only other things in agenda would have been the partial transposition and negativity. But if you know that those things already, maybe I can skip over that and start quantum computation. Not really. It's a completely new part. Quantum computation is a completely new part. Okay, I mean, if they don't, I can also quickly tell without going into negativity. I can tell the partial. So you see, if it was separable state, then you see you could just do transposition on this, which is called partial transposition, and it still remains a density matrix. Okay, because a density matrix partial transposition, you see, what can it do? It can at most change some I to minus I, okay, but it still remains a density matrix, right? A transposition of a density matrix is always another density matrix. It's not the same density matrix because of those I's, but that means that this is still as a whole a valid density matrix with positive eigenvalues, and that's a way to check whether something is separable. So if that is negative, means the state must not be like that and it's entangled. Okay, and this is also used to construct a measure. Okay, so I will end with that today. I mean, it's been super fast, but we will move on to quantum computation next time. Thanks.